In this video, I would like to talk about convolution, which is an important concept in signal analysis. It comes up a lot in this class. The idea behind convolution is simple. We can represent any signal as a superposition of unit impulses, or if we're dealing with continuous time, it's going to be approximation to unit impulses. Then, if we're dealing with a linear time invariant system, its output, the response of the system, is going to be nothing but a superposition of unit impulse responses to each of those unit impulses. So if we know how a system responds to a unit impulse, what's called the unit impulse response of a system, we can figure out its response to any signal. The only tricky part here is that although the input signals, the unit impulses are infinitesimally short duration, so their superposition does not overlap in time, they come one after another, the unit impulse response could be of prolonged duration, and so the superposition of unit impulse responses actually will overlap in time, and the total response of a system is going to be often longer than the input signal of for the system. So with this in mind, let's take a look at a simple example and see how this works out. Here we have two functions, x of t, which is the input function, and that's a unit step function u of t minus 2, which so it becomes 1 when t becomes 0, and then when t becomes 2, so u of t minus 2 becomes 1, and then the x of t goes back down to 0. And the response of the system, which is a similar function except that it's shifted by 2. And now we have to find the response of the system to this input x, which is going to be given by the convolution of x of t and h of t being, of course, the unit impulse response of the system. So now we have the convolution integral. And one thing we need to keep in mind when you look at this integral is that suddenly we now have to deal with two variables. Tau, which is the variable of integration, and t, which is not the variable integration, but the value of the integral is going to depend on it. So to better understand how to do this integral, let's plot them, h of t and x of t minus tau, plot them as a function of tau. Now, h of tau, it's the same as h of t. We just renamed the variable from t, we now call it tau. Now, x of t minus tau is a little more tricky. We see here that tau appears as a negative sign in argument of the function. So it's reversed, right? Now going from right to left. And also it's shifted by t. So this is going to be the plot of x of t minus tau, right? When when tau hits t, it becomes 1, and it would continue to the right, except when when tau equals t minus 2, then the second summand here, u of t minus tau minus 2 becomes 1, and then it goes back down to 0. So when we look at the integral, we have to remember that if any one of these terms is a 0, then the value of the integral is going to be 0, of course. And we're going to see that most of the time axis, at least one of those terms is going to be 0. Now, looking at h of tau, we see right away that tau has to vary between 2 and 4. Because for any other value of tau, h of tau is 0, and the y of t is also 0. Now, the value of x of t minus tau, of course, depends on the value of t. Now, to better understand this, we plotted them here on the same plot, h of tau being in red. And we notice right away that until t reaches 2, as long as t is less than 2, there's no overlap between these two graphs, which means that there's no value of tau where both h of tau and x of t minus tau would be non-zero. So that the integral will have to be 0. If you start moving t to the right, t increases. So if we effectively look at this plot of x of t minus tau is shifting to the right, we see that once t increases past 2, hits 2 or goes past 2, we begin to have an overlap of the two plots, which means that there's a non-zero region where both of those terms are non-zero, and the integral is going to have a non-zero value. And now that region goes from 2 till t. So that gives us the first integral for this y of t. It's from 2 to t of h of tau x of t minus tau d tau. Now, that's going to continue until t hits 4. Once t hits 4 and it goes past 4, we're going to have a different overlap. Now, Again, so the black rectangle shifted further to the right, and now the overlap is between t minus 2 till 4. And that continues until t minus 2, right? The left end of this rectangle hits 4, which means that t has to be 6. So between 4 and t values between 4 and 6, we have this overlap, and this is going to give us the new integration limits here of t from t minus 2 to 4. And that's the second part of the convolution integral. Now, once t gets bigger than 6, of course, we see again there's going to be no more overlap. The rectangle, the black rectangle will pass the red rectangle, and again the value of the convolution integral is going to have to be 0. Now, we have these two integrals, which are very simple integrals and easy to solve, because we know that h of tau and x of t minus tau, whenever they're non-zero, they're 1. So it's going to be simply d tau, and the integral of that is tau. And integration limits being t and 2. Here we get t minus 2 for t going between 2 and 4. And for t varying between 4 and 6, it will be going, again, same integral, the limits of integration of 4 to t minus 2. And we get 4 minus t plus 2, which is 6 minus t. Now we can easily plot these. These are two straight lines. The first one has a positive slope. Of course, it's 0 when t is 2, and when t is 0, it's negative 2. So we could draw this line. That's going to be given by the blue segment here. And the second integral gives us a line with a negative slope, as t is negative here, which starts from 6 and goes to when t is 0, y is 6, and when t is 6, y is 0. So these are two lines represented by these two equations, and now we see that the convolution integral is going to be 0 until t is 2. From 2 to 4, it's given by the blue line. From 4 to 6, it's given by the red line, and again after 6, it is 0 again. So this is going to be the answer to our question. This is the convolution of these two functions, and this is the system response of this system to this input. And a couple of things to notice here is that duration of this response is now 4 units, from 2 to 6. Although the input duration was, if you remember, the input duration was from 0 to 2, only 2 units. And the other thing to notice here is that the value, the maximum amplitude of this response, actually hits 2, although the amplitude of the input signal was only 1. And again, that's a result of that summation of all the superposition of all these unit impulse responses to each of the input impulses. Thank you very much for watching.